Log on, tune in, find out. Another good idea from Cambridge.
Instanton calculus and quiver gauge theories.
Okay, thank you very much. I'm happy to be here in real Cambridge for the first time, and it's a nice experience. So thank you organizers for making this conference. Today we'll talk about the subject of 4D n equals 2 gauge theory. Computing its low energy effective action by doing a microscopic calculation of instantons, summing over all instantons in the theory. So we restrict our attention to the theory with the gauge group, which is a product of UN gauge groups. Product of capital Ni for I running from 1 to small n. And so vector multiplet is determined by that gauge group, and hypermultiplet is determined by representation of the gauge group. And for representation, today we take a sum over fundamental and bifundamental representations. Fundamentals and bifundamentals. So such theories are known as quiver theories, and conveniently the Lagrangian is encoded by what is called quiver diagram, so that to each gauge group you associate a node, and a link for every bifundamental representation which connects to nodes. Now, as you probably know, all such theories can be obtained as a special limit, as a degeneration limit over quite a listable class of theories, which are called ADE n equals to superconformal field series. So there you contain quivers. There you consider quivers. I will draw actually the list of all of them. So that's D series corresponding to orthogonal affine groups. For E series you have three exceptional quivers: E6, E7, and E8. So actually, let me put heads here, as I'm talking not about the regular finite algebras, but about affine algebras. So I distinguish that by putting a head. And the nodes in those quiver diagrams are labeled by Dynkin numbers, so which just count the integers in the decomposition of the special delta vector in the Lie algebra. And let me put those numbers here. So it would be 1, 1, 2, 2, 2, 1, 1 for the D series. For E6, that would be 1, 2, 3, 2, 1, 2, 1. Here it would be 1, 2, 3, 4, 2, 3, 2, 1. and there it would be 1, 2, 3, 4, 5, 6. Well, we just said that in a second. So what those numbers count? Sorry. So what I want to say? I want to say that any gauge theory with a product of UN groups and matter in fundamental or bifundamental representation can be obtained by taking a limit where you decouple one of the gauge groups here by sending coupling constant associated to one of the nodes to 0, so that the dynamics is frozen, and for the remaining gauge groups the dynamic is still computed. And also fundamental multiplets can be regarded as a bifundamental multiplet with respect to one of the gauge groups for which the dynamics is not frozen, and as a fundamental for the one for which the dynamics is frozen. So you can represent any of those theories as a special limit of one of those types. So first I drawn you separately the quivers which have a topology of tree with no cycles, and to the separate case stands AN hat quivers, which look like a cycle. So this is example of 0, 1, 2, 3, 4, 5, 6. So this is what is drawn here is A6, and those labels just enumerate vertices. Concerning the Dynkin numbers, which we are written here, they are all equal to 1. You'll put them in circles probably. What these little numbers at each node encode, they encode the ranks of the gauge groups. Namely, we take an A and I, the ranks of gauge groups, to be equal AI times some fixed number n. And under this condition, the resulting theory is superconformal. Its beta function vanishes. Well, the reason that there is only such finite list of theories is that the beta function, if you compute it for each node, it goes like to an I for the vector multiplet minus the sum over links in J. If you denote the number of links from the node I to J as minus AIJ, then you see that beta function is just contraction AIJ and J. And now you're looking at the problem of finding a list of positive integers and Ij such that the beta function would be non-negative. So if you want UV asymptotically free theory or UV conformal theory. So therefore you end up with the same classification as the classification of Dynkin diagrams, and that's why you have just a finite list of the theories. So so that's why we restrict our attention even when we talk about arbitrary quivers. We can actually just solve the problem for these theories and take all other cases as the special limits of that finite list. Yeah.
Quiver by gauging some node. Because what if you have a theory which would have a quiver with two loops, for instance?
Yeah, you can't have theory with two loops. It would break this condition of the non-negativity of beta function.
Yeah, but in your original setup, you're also considering conformal theory. Ah, you want. Okay. You want
So, for example, if you try to make like like two loops, then if you compute beta function at this point, it would be negative because there are too many nodes. Well, I can prove you why there is only this finite list, but it goes in exactly the same way like you prove classification of Dynkin diagram for Cartan algebras when you classify them into finite, affine, and hyperbolic types. Do you have some specific example in mind?
But I would imagine if you compactify the 2-0 theory on a surface of genus larger than.
So that example is it's not representable as a quiver theory with the hypermultiplets in bifundamental or fundamental representation. It is more well exceptional type of theory. It's not in this class. It doesn't. It's not bifundamental or trifundamental representation. For the matrix, some different representation. Yeah, and we are not talking today about those theories. So just those conventional types. So nothing like that. Okay, where is razor here? Okay, so the goal is to compute n equals to low energy effective prepotential. Prepotential curly f, which is a function of the following parameters. It is a function of A, the Coulomb moduli, of M, the masses of hypermultiplets, and tau, the coupling constant. And each of those letters encoded n tuples of parameters, so that A is a list of vectors AI, where AI is in the Lie algebra of the corresponding gauge group. So it's that complex vector in the associated vector multiplet. M is the list of bifundamental masses between the nodes ij, so for those I and j which are linked, and tau is the list of coupling constants. Well, in the usual parameterization where tau, the complexified coupling constant, is 4 pi I over G Young-Mills squared plus theta over 2 pi. So it seems like a daunting task to try to integrate over Instanton module space, especially as the Instanton number grows larger. Those who try to do that integral of repeat original computations consider it becoming very hard, even if you go to 2 instantons and so on. Fortunately, a way to do that nicely was found, that starting from the works by Mur, Nekrasov, Lossev, Shatashvili in the end of 90s, and then Nekrasov completed their program by summing all instantons for theory with with a single gauge group, and then Nekrasov and Takhunkov proved actually that that sum corresponds to Seiberg-Witten solution. So what we are doing here, and well, I'm sorry, I forgot to put the title. This work is in collaboration with Nikita Nekrasov. What we are doing here is completing the same program for arbitrary quiver theory with fundamentals and bifundamentals. The idea is the same as in the work by Nekrasov-Okrenkov. We extended that work to this more complicated case. So let me just quickly review the formalism. There, to find the low energy effective prepotential, you essentially compute first the partition function Z of the theory in the so-called omega background, which means that you take the space-time to be Euclidean space R4 and deform the action and the theory and the supercharges, supersymmetries of the theory by combining supersymmetry with the Lorentz rotation SO4, well, actually broken to U1 cross U1, where each of those U1s rotates two plane. So R4 would be C2, let's say with coordinates Z1, Z2. So that's Z1, Z2. And let's say the generators of U1 are denoted by T1, T2. So one action on the space-time is given by Z1 mapping to T1, Z1 and Z2 mapping to T2, Z2. And the standard notations for those generators of U1s, for those equivariant parameters, is T1 equals exponent of I epsilon 1, T2 equals exponent of I epsilon 2. So after such deformation, the theory effectively becomes confined in a box, well, like a smooth box, a well, essentially quadratic well of the characteristic size 1 over characteristic volume 1 over epsilon 1, epsilon 2. So therefore, since the theory is in finite volume, its partition function is finite, doesn't have infinity associated just with the integration over infinite volume, and you can compute the partition function itself, and it would have the limit as epsilon 1 and epsilon 2 goes to 0. The partition function has a limit from which you extract the low energy effective prepotential, namely in this limit, Z is exponential of 1 minus 1 over epsilon 1, epsilon 2, the prepotential over the theory. So this function depends on parameters, on the same parameters, A, M, tau, and in addition, the parameters epsilon 1, epsilon 2. So that's the object that we want to compute explicitly by summing over instantons. How are we going to do that?
Sorry, can you just
Yeah.
explain? You say it's confined to something of that size. But if I look at those epsilons, then I can do epsilon 1 goes to epsilon 1 plus 2 pi n. Can't I? And it's the same phase. Sorry, I'm confused.
Sorry, I meant
Something?
no, I meant okay, epsilon goes to epsilon plus 2 pi n. Yeah, good question. Let me try to answer later.
Okay. I mean, could you just give some intuition why it is confined? Because at the moment, I just see that thing being a phase. And
Well, the intuition why it's confined is that if you write down, okay, maybe a short answer to this question is that even though here you look at epsilons exponentiated as the generators of group action, in fact, when you do the theory in 4 dimensions, it's better to, well, in practice, they are Lie algebra generators. And the deformed action of the theory, it is quadratic in epsilons. It's not a function of exponentials of I epsilons. It's just the extra terms which are added to the Lagrangian, they are linear and quadratic in epsilon, not in T. That's what happens in 4 dimensions. There is another part of the story which is called which has a name of like K-theoretic version of this partition function or 5-dimensional Young-Mills, and there is an extra circle, and there indeed there is a symmetry associated to shifting epsilon by 2 pi m. But in 4-dimensional case there is not. Yeah.
Don't you want to say that this is the equivariant volume of R4? 1 over epsilon 1 times epsilon 2 is the equivariant volume of.
Yes, I want to say this is equivariant volume. In 4-dimensional case, epsilons, they are Lie algebra generators of the U1 action of the theory, and you think about them really the Lie algebra parameters, not the group parameters. So I wouldn't write explicitly the action, but just schematically the action in the omega background is the original action plus some correction of the order epsilon plus some correction of the order epsilon squared. And those terms of the order epsilon squared, they effectively confine the theory to a box of size 1 over epsilon 1, epsilon 2. Okay. So what's going on mathematically is the following computation. I mean, the partition function of n equals to gauge theory, from a mathematical point of view, is the following homological differential geometry like object. The partition function z, like the integration over all fields with corresponding action, is the following. It's the sum over instanton charges, which I collectively denote by k. So k, again, is the list of charges, k1, so on, kn for all groups. And then you integrate, so you fix the second Chern class of the corresponding vector bundle to be, so C2 of the corresponding factor, let's say epsilon I equals ki. You take q to k, where q is the list of exponentiated coupling constants, exponential of 2 pi I tau, that comes from the integral of f which f, the instanton charge contribution to the action. And the remaining thing is the integration over the space of the connections modulo the group of gauge transformations. So curly A is the space of all connections, and curly G is the space of gauge transformations with a fixed asymptotics at infinity. I mean, with fixed equal to 1 at infinity. And what is integrated is equivariant Euler class of the following bundles. From the vector multiplet, you have the bundle of the self-dual 2 forms in a joint representation, and this comes from the terms in the action like f plus a squared. Well, essentially, you know, like Poincaré-Hopf theorem, that you can compute Euler number in two ways. Either you can integrate differential geometrical class or differential geometrical form representative of Euler class, like curvature, or you can just sum over zeros of the corresponding vector field. So here you sum over zeros of the bundle whose sections are given by f plus. So the zeros of f plus are instantons, and the integral reduced to the integral over instanton module space. Equivalently, you write it as a Euler class of the corresponding bundle of self-dual 2 forms of the space of all connections. So this part describes vector multiplet, and then equivariant, similar equivariant Euler class for the bundle of spinors. Actually, it's virtual bundle of left spinors minus right spinors given by Dirac operator in the corresponding representation R associated to the Hiver multiplet. So that's what is the gauge theory Lagrangian looks like if you represent it in a cohomological way. And what is T here? T is the following torus. It's the maximal torus of the gauge group at infinity, which is not included into this factor. So it's a finite gauge group, that the product of UNs times the torus associated to the flavor symmetry, whose parameters are masses, and the torus associated to that SO4 action on the space-time, whose parameters are epsilon 1, epsilon 2. So we can call it Lorentz. So the parameters of those would be A's, masses, and epsilons. All those Euler classes are computed with respect to that equivariant action. Excuse me? That has everything inside. What is written here has everything inside. In fact, as you see, the bundles which are written here are the bundles of infinite. These are infinite dimensional bundles over infinite dimensional spaces, and you can reduce that to the one loop factor times equivariant Euler classes on the finite dimensional spaces, like instanton modular spaces, and finite dimensional vector bundles over. That's what I'm going to write in a second. Finite dimensional vector bundles over instanton modular spaces of the corresponding zero modes of the Dirac operator in a given representation R. What is written here is before reducing to instanton modular spaces. It's just the original path integral of the gauge theory. So this is path integral over the space of connections and all other fields. It just has this reinterpretation as in terms of cohomological classes. Okay, so for computation, we are, well, you know that instanton modular spaces, they behave not very well when instances degenerate. When you go to the boundaries of instanton modular spaces, when instantons shrink to zero sizes, there are problems, and we want to have a nice compactification of those instanton modular spaces. And for the compactification, we use Giesecke-Nakajima compactification. In physics, it's known as a compactification by U1 instantons, or non-commutative space-time. That is the situation when you can consider U1. Normally, you don't have like physical U1 instantons, but in non-commutative theory, you might imagine you actually can construct a connection with a non-zero C2 and U1 gauge group. Mathematically, they correspond to to compactification by torsion-free sheaves, and those U1 instantons are ideals which are supported just in one point. So anyways, we don't actually need those concrete mathematical details of that. We just employ the usual ADHM description of the Instanton modular spaces. So I will remind you. How it goes to, or actually to compute those Euler classes. So here, the space V. So here I'm writing down ADHM data for Instanton modular space MK of UN gauge group. Now V is just a complex vector space of dimension k, and W is complex vector space of dimension n, and M here is the space-time, which for us is C2 or R4. So this is a DHM triple, the complex from V to V tensor M plus W to V, and those maps are encoded by ADHM, what are called IDHM matrices. So here we have the matrices B1, B2, which map V to that term, to V tensor M, and matrix J, which maps V to W. And here we have matrices minus B2, B1, I. So the condition that this map is that this mapping is a differential means that the square is 0. So these are the usual ADHM equations. And now the Instanton model space is the space of such matrices B1, B2, Ij modulo GLK transformation of the vector space V. Okay, so what you want to do, well, as was already mentioned, there is an infinite dimensional factor in those Euler classes, which has physical interpretation as a one-loop factor. It can be factored out. What remains is the sum over integrals over Instanton modular space is the sum over such guys MK. So we need to integrate over the space of those matrices and sum the series. Actually, it's possible to do all that work in a compact way, in an efficient way, including the Instanton factor. So, sorry, including the one-loop factor in a just in one formula, and for that you just use from the construction of the ADHM Instanton modular spaces. We know that the fiber of the corresponding vector bundle, which is described by a given triple of ADHM matrices B and Ij, is given by the cohomology of that ADHM complex of what is written on top, with the matrices Bi corrected by subtraction Zi, so that's the fiber at the point Z, say Ij. So what's the strategy? We want to compute those Euler classes, and it's convenient first to compute Chern classes by writing the sum over exponential of corresponding weights, and then convert the Chern classes into Euler classes. So here, the Chern class of the corresponding ADHM triple would be well, you just sum Chern classes in the middle and subtract zeros and the last term of the sequence, and you get Churn t of w minus churn t of v times churn t of m minus churn t of lambda squared of m. Here the last term should be actually written as v tensor lambda squared of m. It doesn't matter when you consider that complex on itself, but when we consider it equivariantly with respect to the rotation of the space-time, the last term actually should be corrected by O tensor lambda squared m minus 1. Now, what are ingredients here? Well, the Chern character of the W of the space associated to the fundamental representation of the gauge group is just the sum over exponentials of IA alpha. Chern tau of V is the sum over exponentials of I phi I, where I runs from 1 to k to the charge, and here alpha runs from 1 to n to the rank plus 1 of the gauge group. And Chern t of m of the space-time is just the sum over two exponentials of epsilon I plus epsilon 1 plus exponential of I epsilon 2. Okay? So this is a concrete expression in terms of those exponentials, and that's almost enough to actually write down what the Euler characters are. So actually, let me denote it. This is by epsilon t. Okay, so we need the Euler characters of those infinite dimensional bundles fibered of the space of connections, and for that we use Atiyah-Singer theorem, or also in this connection it can be thought as a Hirzebruch or even Roch formula. It's the formula for the index of the corresponding differential operator. Well, you can observe that those complexes of self-dual forms, or just Dirac operator acting on positive or negative spinors on space-time, those operators can be viewed as a twisted Delbo operators. So what we need to find the index of that Delbo operator equivariant with respect to the T action on the space of sections, and it can be equivalently thought as a Chern character of the cohomology space of the corresponding bundles, like omega, like the bundle of that omega 0 to omega 1 to omega 2 plus associated to vector multiplet, or simply S minus to S plus with the Dirac operator making here associated to hypermultiplet. Anyways, for those guys, we find the Chern character of the cohomologies by integrating equivariantly thought class of the tangent bundle to M to the space-time times Chern character of the associated vector bundle. So this depends on representation. So let's say if we are doing vector multiplet, then here we would take epsilon times epsilon star. If you are doing a hypermultiplet, for the link between I and J, we would take the same thought M Chern equivariant with respect to T of epsilon I tensor epsilon j. And if mass of this hypermultiplet is m, then also you should include that m in the computation of the corresponding Chern character. So the integration is trivial in the equivariant setup because third of equivariant of the space-time is simply 1 minus e to minus I epsilon 1, 1 minus e to minus I epsilon 2, here I epsilon 1, I epsilon 2, and the equivariant integration over m of some equivariantly closed form gives you, well, with respect to the fixed point at the origin, gives you a factor 1 over epsilon 1 I epsilon 2. So as a result, the Chern characters of their of those infinite dimensional vector bundles that we are interested in are given by the following. So let me call it chi associated to vector multiplet parameter t is just 1 over minus I minus epsilon 1, 1 minus I minus epsilon 2, multiplied by et e minus t. And for hyper, for the bifundamental, it would be the same prefactor multiplied by et e minus t between the nodes I and j. Okay. Now, well, now if you plug that formula into this formula and expand the denominator in the power series of exponentials of epsilons, you will get infinite Taylor series, and they correspond to, of course, each term in this series correspond to the mode of the fluctuation in the physical fields in the series. So the product of weights in the exponents for each of that mode would be the one loop determinant for fluctuation in the normal directions to the Instanton modular spaces. We want a compact way to represent that procedure, how to convert the sum of exponentials of weights into a product of weights, and it's conveniently done by the following integral transformation. Let's say that Chern T of some space is the sum of weights, and we want Euler class as the product of weights. So how do we convert the sum of exponentials into a product? Well, we just use the formula for the gamma function. So it's w to minus s is the integral 1 over gamma of s, integral from 0 to infinity d tau t to s minus 1 e to minus tw. And from here you see that the Euler t of some t module w is exponential of minus d over ds 1 over gamma s. And here you integrate by dt with the weight t to s minus 1, your Chern character of the space w. Okay. So we are almost done. What we are left is to plug in the expression for Chern characters of those of the spaces with fluctuations into that exponential transform. And because in all those Chern characters that we have here, there is this denominator, we would like to factor it and denote and introduce a function. Well, this function has a name as a special function, Barnes factorial function with parameters epsilon1, epsilon2. It is defined as the function of complex variable x as an analytic continuation of the integral. Well, you should really take that, evaluate the derivative at s equals 0. So this is an analytic continuation of the following integral 1 over gamma of s dt t to s minus 1 1 over minus I t I epsilon 1 1 minus I t epsilon 2 e to I t x. So if you expand that in Taylor series, the denominator, assuming that, let's say, t has a positive imaginary part, then you can expand and the expansion converges and integrate each term. You will get like the sum over 1 over x plus epsilon n1 epsilon 1 plus n2 epsilon 2, the power s's. So this is like zeta function associated to the one quadrant in the two-dimensional lattice. Okay, and since you take d over ds, then you would get logarithm of the product of those factors. So this is a generalization to two-dimensional lattice to one quadrant of the usual gamma function, which has poles as at every negative integer and 0. Okay, so this function appears from this point all the time in the computations. And now, well, if you just take that formula for the Euler character and the definition of this gamma function, and also you introduce Fourier transformation for the for this character in the fundamental representation epsilon t. So let me give it a name, epsilon t. Let me introduce parameter t for Fourier transform, and the Fourier transform would be called density. Well, in practice, for a finite number of instantons, the density is just the sum of delta function. So it's the sum of delta function like x minus a alpha minus like delta of x minus phi, and so on. Some delta function corresponding to the v term are written here, and the w term are written here. Well, anyways, we want to take the infinite number of the limit of the infinite number of instantons, and in that limit, the sum of delta functions in the densities is approximated by a smooth function. So we want to solve that the limit shape problem as the number of instantons goes to infinity, and when rho from the sum of delta functions becomes just the density support like of charges on each interval around the corresponding Coulomb parameter A alpha. So let's say A alpha here. This is x axis, and here we have some density support of rho. Okay, so let's actually write down that extremal energy problem. Well, just from the definition, first of all, from the definition of the density, you can see that it is restricted by the condition that rho of x dx over each interval is 1. The first moment is fixed to be equal to the Coulomb parameter, and the second moment, you integrate over the whole space with the sum of all supports is equal to the second Casimir sum of a squared minus corrected by the Instanton number by 2k epsilon 1 epsilon 2. So since we want to sum the instantons weighted with the classical action and weighted with their Instanton number, we should add this term to the effective Lagrangian in terms of those instanton densities. And the Lagrangian itself, of course, is bilinear in rho, as can be seen from here. So let me write it down, actually. So that Euler determinant associated to vector multiplet is now exponential of the following bilinear in the densities contracted with the kernel, that gamma function. So it's rho of x, gamma, x minus x prime, rho of x prime. And if I write it for ith factor, ith gauge group, then here we take ith densities. For hypermultiplet, it's more or less the same, just the opposite sign, because the statistics is exchanged between fermions and bosons regarding to this cohomological interpretation. So it's dx dx prime, rho I of x, gamma of x minus x prime, or j of x prime, and generally it is shifted by mij by mass of the corresponding hypermultiplet. So altogether, this can be combined Okay, let me actually restrict to the case when there are no cycles in quiver, or sum over cycle of masses vanishes. Then you can always find such masses mi that each mij is represented as mi minus mj, and then you shift x to x plus mi for each gauge factor to remove the term. So after that, it's possible to write down their effective action in a very compact way, so that the partition function is the integral, well, is the exponential of this bilinear contraction, integral of dx dx prime, then matrix aij, which encodes how many hypermultiplets you have between the node a and ij, which has 2 on the diagonal. So this is Cartan matrix of the corresponding quiver. And then it's simply rho I of x, the kernel gamma of x minus x prime, or j of x prime, and that's it. Whoa. And plus the term which counts instantons that one, x squared rho of x dx, so plus 1/2 logarithm q I integral rho of x squared dx. So that's the that's the effective action in terms of densities. So the exact result is the integral now. The exact partition function is the integration over all densities with that action. We want to find it in the limit when epsilon1, epsilon2 goes to 0, just to restore the Seiberg-Witten effective prepotential. And in that limit, as I said, we can just extremize that effective action with respect to rho. So we extremize by taking the variational equation delta rho equals to 0. Well, there are also Lagrangian multipliers associated to the constraints that I have written for the 0 and first moment of rho. It's convenient to get rid out of them by taking the second derivative after you take the variational over rho. And then if you do all that, you get a very simply looking equations, namely on each. This is like in the matrix models. So you would have cuts which support the densities, and let me introduce the integral transform of the density, the functions vi, which is rho of x prime, second derivative of that gamma function x minus x prime dx, and what is essential is just the second derivative of gamma function in the limit epsilon1, epsilon2 goes to 0. It's simply 1 over epsilon1, epsilon2 logarithm of x. So it's simple logarithm kernel transforming the density. So now for this logarithmically transformed quantities vi, the variational equations have the following form. If you denote vi minus and vi plus, the values of those integral transforms on the upper side of the cut and lower side of the cut. Can I have 3 minutes? Okay. If you denote it like that, then the equations are that vi plus vi minus of x equals to logarithm qi minus sum over j equal y aij vj. You get straight from that formula. All right, now we want to look at them at slightly different angle on these equations. We look on them as equations. We determine how much the function as a cut crossing transformation. What happens if you cross the cut, how this vi function changes. So vi plus goes to vi minus, and this cut crossing transformation now has the form that vi on the cut crossing goes to vi minus aij vj plus logarithm qi. Maybe I'll be just a bit schematic next, but I think you from here you already see that it has to do with Weyl reflection of the associated to the quiver of the associated Lie algebra to the quiver, not the gauge group but the quiver, those which I pictured in the very beginning. AN, DN, E6, E7, E8 heads. So that transformation is Weyl reflection good. so if it's while reflection, and we want to find a function, we want to find analytical function on the complex plane, which is, well, the function v from the definition can be seen that the only singularities of those functions are on the cuts which support the densities. And if we construct now invariant while of g hat invariant, of those vi functions, this while invariant has to be analytical function on the whole complex plane. So it's analytic function on C, well, with that coordinate x. Moreover, we can easily find the behavior of that analytic function at the infinity. Well, if you take concrete while invariant. What while invariants can we take? We can take characters, let's say in the fundamental representations associated to the nodes of the diagrams. And from the asymptotics at infinity of those characters, you find that it has to be polynomial of degree ni associated to each to the rank of each gauge group of x. So this is the answer. Actually, this is the final answer. I don't have more time to write it down more concretely, but it's already computable formula. So this is once again, this is a fine character of the Lie algebra associated to the quiver, that ADE series. This is just polynomial nx, which has unfixed ni parameters. The highest term is fixed to be x to ni, and then there are unfixed parameters. They are Coulomb moduli. So this equation defines to you the functions v of x, and finally the subject-Witten differential, which computes the integral of the densities is x dx. So it has the form lambda Seiberg-Witten would be simply x dv 1 over 2 pi I. So integrating that expression over the corresponding cycles, you get the values of Coulomb parameters A, and for the dual cycles gives you differential of the prepotential f of the corresponding A parameter. Shall stop here. Thank you very much.
Questions?
Interpretation of the higher order epsilon correction are just graviphoton contribution. If I remember well, there's usual case there's a higher order epsilon. The deformation are computed by topological strings. They're graviphoton polarization basically, right?
Sorry, the question is about epsilon corrections to the prepotential.
Yes.
And what exactly the question about those epsilon corrections?
The graviphoton.
Yeah, they well, in the limit, in the special limit when epsilon 1 equals minus epsilon 2, and if you lift the theory to 5 dimension, it's known that this equivariant partition function is equal to the topological string partition function in the geometrical engineering picture. As a type 2A on a local Calabi-Yau, the topological partition, A model topological closed string partition function, which computes Gromov-Witten invariance for those geometrically engineered local Calabi-Yau spaces, is equal to this gauge theory partition function. So what you can think about the transformations which are presented here is like it is like proving mirror symmetry in this specific context. You start from the A model like sum over instantons, which correspond just to the string theory, I mean the topological A model instantons, and you convert the infinite sum into some complex analytic geometry describing effectively the B mirror of the theory. So on the right hand side, so this is the B-like model geometry, and the original is A-like model geometry. And this is done in the genus zero approximation. Like epsilon corrections, they correspond to the higher genus correction of the topological string.
Any more questions? Okay, thank you.
Okay.